Hi there. I'm over here, down here. You can see me, well, I'm also over here. But the difference is, this is just a webcam, and this is a webcam running on my Raspberry Pi with a neural net that is capable of detecting 7 different emotions, and as you can see on the display, feeding back which one it thinks you're doing at the moment. Now, it can detect 7 emotions, which are neutral, anger, happiness, sadness, surprise, fear, and disgust. I think that was 6. Maybe that was 7. But anyways, I can do a good happy face. And you'll see it says buzz buzz every time it changes, and I'll explain why that is in a second. Here's my angry face. And I just learned how to do surprised. It's kind of tricky. You gotta like open your mouth a little bit and look to the side. Weird, right? I think we're still a little bit smarter than the machines, although I can't really I can't really fake a sad or disgusted face yet. Maybe that's a superpower. I can't force myself to be sad for no reason. I don't know. Anyways, the whole purpose of this project was to work on implementing a neural network, but also for me personally, I think emotional intelligence is one of the biggest predictors of success in life and work, and noticing and reacting appropriately to somebody's emotions is a big part of that. And I think one of the things that that people are not so great at is being present in the moment and really paying attention to the person that they're talking to. So while a human brain is very good at recognizing emotions and seeing reading a person's face and reacting appropriately, computers are not quite there yet. But the good thing about computers is they never get tired, they never get distracted or drunk or anything like that. So while the computer is always watching and monitoring at the same level of effectiveness, it can kind of like alert you that something happened. So in the case of this demo here, it's kind of watching me all the time, and then it's giving an alert in the case that my emotional state changes. So that would be kind of like a tick to say, hey, pay attention, something's going on with this person, maybe you should address that, or bring yourself back to be more present in the moment. And the cool thing is, of course, that this is done on a Raspberry Pi, so it's a computer that could fit in your pocket. It could potentially become scaled down to a wearable. We're using TensorFlow Lite, and it runs reasonably fast with this size resolution, and I'll show you some ways that it can actually be improved later on. Okay, so here's a little slideshow that I made just to talk about what the thing is. It's built on a Raspberry Pi version 4. We got the Raspberry Pi camera. This costs about 20 bucks if you want to buy one. It doesn't come with it, but you got to buy it separately. And then I made this little buzzer, and this is just for a demo to simulate like a wearable device, you know, to say it's gonna buzz every time you detect a change in emotion, instead of looking at the output on the screen the way we were in the demo earlier. This, I just 3D printed the enclosure, and it's literally just a vibrating motor and a transistor. And that's it. Yeah, I was thinking about putting a resistor in there to control the current, but I don't think there is one. I think it's just what do you mean you don't know? You don't remember? I mean, I haven't opened up the box in like months, so maybe there's a resistor in there. I don't think so. Okay, so this is a picture of the setup. You have a Raspberry Pi version 4 and the Raspberry Pi camera. This thing doesn't come with it, you have to buy it separately, but it's not that expensive and it's totally worth it. It's a really good camera. And it actually, if you're not running the neural net on there, it runs a lot faster than you saw in the demo. And then this is my buzzer. This is just a 3D printed enclosure that I made with my Washington Huskies logo, and all it is a vibrating motor and a transistor inside there. So what does the device do? It's got to capture audio or video stream with the camera. It's got to analyze the faces, classify their emotions. It's got to do it quickly. You saw the FPS tracker. And then it's got to provide feedback to the user via the buzzer. Now the reason I use the buzzer instead of just the printed output that you saw in the demo is that I'm trying to simulate like a wearable device where instead of watching the screen for the predictions, you'll just feel a little buzz to alert you that something happened, that there's some change in emotional state that you need to pay attention to. So how did I train it? So basically, if you go to Kaggle, if you're ever trying to find some kind of data set or something like that, Kaggle has these machine learning competitions where they will post the data set, and then it's an open competition. You just make your model, train it, and then submit it. So I just went in there and typed in emotional detection or something like that, and it came up with this one with the FER 2013 data set, 28,000 labeled examples. Awesome, exactly what I needed. So so that's where it came from. I ended up using this 7-layer. Oh, and so if you are really new to machine learning, all you have to do is go on there, and there are some examples on there also. So people have put their submissions on there, and then they upload their code and show exactly how they did it. So it's super helpful if you're just starting off. So when I was just trying to get something that works, just to load anything onto the Raspberry Pi before even worrying about making a classifier, I just downloaded one that somebody had put up as their solution, and then I transferred it onto my Raspberry Pi. So that's the quickest way to start. Eventually I got to this 7-layer convolutional neural network with the F1 score of 0.7. And so here's some examples of the training data. It's 48 by 48 pixel grayscale image with the label. And here's the score results. So this thing, and like the cool thing about Kaggle also is that all this visualizations and these kind of like metrics are all there already. Somebody did this, so all I had to do was, once I trained my model, they already had the code to evaluate it. So this thing is kind of cool to look at. So you have the true labels here, and the numbers correspond to some emotion, and then you have the predicted labels here, so you can see that like the darker ones are the ones that are very good, that it's very good at predicting, right? So this one corresponds to happiness, almost always gets happiness, right? Let's see, and then you can even go up here, precision and recall, okay, maybe not almost always, but 89% of the time, or 88% of the time. So precision and recall, what that is if you look at, say, the true label is 3, but sometimes it guesses other things. So those would be false negatives. And then you look at the predicted label of 3. These are all the times when it predicts a 3, but sometimes the true label is something else. So those are false positives. And that's precision and recall. So by doing this F1 score, you're combining both of them together. And that takes into account both false positives and false negatives. So the first problem that I ran into when I was building this is as soon as I put the model onto the Raspberry Pi, nothing worked. It had a decent accuracy score on the test validation data, but the problem was the training data had very close cropped pictures of faces, and in reality, when I'm looking through the camera, what I see is something more like this, where my face is a very small percentage of the total image, and the neural net really didn't know what to do with that. So I realized just by cropping it, you would give it something that's more similar to what's in the training samples than what it's seeing straight out of the camera. Then I tried this experiment, which was to say, okay, if I crop it, but I crop it not so well. So I did these crops manually, but you can see, and some of them are stretched and stuff too. But the good news is most of them worked, except for the really bad, okay, this one, he's not even in the picture. And then this one missed most of his face. So maybe he's not smizing enough. So the good news is you don't have to crop very well. You just have to crop pretty close to the head. So what I ended up using is this thing called Viola-Jones Cascade Classifier. And this is actually built into OpenCV. So it's very easy to implement. It's basically just like a few lines, and all it does is it takes the image and looks for these features of light and dark. And they found that these features, like dark on the eyes, lighter on the cheeks, kind of like lighter on the nose, these kinds of things translate very, very well to human faces. So this is a program that just takes in the image and then it returns bounding boxes around the faces. It will do multiple if there's more than one found. But for me, I just needed one, so I just take the first one and send that, resize it to 48 by 48, send that to the neural net, and look for the emotion on it. Works so much better. The accuracy is great. The speed is great. In fact, in this paper, they talked about how they were running it on a Pentium 4 computer. So this is back in 2000 or 2001 or something like that. And it's running on a computer that's much slower than my Raspberry Pi. Only 90s kids would remember Pentium 4s, right? It's pretty cool. So this algorithm, super fast, very good at finding faces. It doesn't actually tell you anything about the face. It doesn't detect the emotion or do facial recognition or anything like that. It just says that there is a face here. And then on using that small area of the image, I can run my emotion detector thing. So, and actually, when you think about it this way, as this is the process for getting a emotion out of an image, it makes like really, I guess, intuitive sense. But this is how RCNNs work. There was a lot of challenges early on with getting a neural net to classify images for different objects like chair, book, whatever, boat, couch, until they started using this RCNN structure, which kind of like segments the image into like the important spaces. And this is like a very special case of that, where you're just segmenting for faces and you run your convolutional neural network on that segment. So in this case, it was pretty obvious that this is what you have to do, because that's just the nature of how it was trained on just cropped faces. But this is actually a very common thing that people find useful. And so I just wanted to close out by showing this list of things that I learned for the first time doing this project. Before I started this just a few months ago, I had never used a Raspberry Pi before. I never used Linux, GitHub, SSH. I had never used TensorFlow specifically or TFLite. I think that was the most complicated thing about this part, was how do you convert the models into TFLite and then save them onto the Raspberry Pi. OpenCV, love it. It's super easy to use, very good. And then I also learned how to 3D print recently in how to do Fusion 360. So that's just a hobby, and that's fun. I could have done the project without it, but so if you are trying to learn any of this stuff, I will put links in the description to. I have a link for a Colab notebook that I did to train the model. You'll have to download the data set. If you don't want to do that, you can just download the model. I'll put a link to the model in my GitHub, and then you can download the Python program that runs on the Raspberry Pi, and that's all you need. Well, you need to install the dependencies too, but you can run, if you have like OpenCV, TensorFlow, all those kinds of things on your Raspberry Pi. All you need is to download the Raspberry Pi Python program and then the model file, and you can always drop in your own model file or whatever you want. You could even drop in like an object detection model or any other kind of model, and it will work just as well. So that's on the GitHub, and yeah, it's super easy to get started. I hope this makes it less intimidating for people, because machine learning is very complicated. There are a lot of things that you have to kind of get used to that are different than normal programming. But once you get used to it and once you feel comfortable with it, like the cool thing about machine learning is that it does not have to be perfect to work. So in this case, this model that I trained is not the best. It trained in about half an hour, so it's very quick and easy to do, but it works. So you can always make it better once it's working. It's not like a typical program where the algorithm has to be perfect before anything will happen. You can use a suboptimal algorithm, and that's actually what makes this really cool. And you can actually optimize for speed so that you can run it on an embedded device instead of on a GPU.